Hello friends, welcome to lecture 4.1. This is the first module in the unit on time frequency analysis, that is on the foundational concepts of time frequency analysis. This is where our formal study of time frequency analysis begins. In this particular lecture, we are going to talk about the concepts of duration and bandwidth in a formal manner. We have seen these concepts before, at least in a qualitative sense. We have some feel for them, but today we will learn their formal definitions. So, the objectives of this module is to learn the fundamental concepts of time frequency analysis, not all of them, but this is the first module in the journey. Specifically, we will look at the moments of energy densities namely mean time and duration, and mean frequency and bandwidth. A lot of these definitions are easy to follow, again if you draw analogies with probability density functions, as I had mentioned in the previous modules as well. Now, one of the prime purposes of time frequency analysis is to know what frequency content is present in a signal, if not at a particular time instant, but over a small interval of time. So, until now we have seen, at least through a couple of examples in the previous module like unit particularly, that the Fourier transform or particularly the spectral analysis is unable to give us that piece of information. So, let us recap this example in that context. So, this is an example that we have seen before in the context of the continuous time Fourier transforms, where we have a signal that has no activity in the beginning and the end, and in the middle or somewhere in the center we have a couple of cycles of a sine wave of a given frequency. Now, when we say duration, or when we are looking at moments of energy density in time, we are interested in knowing what is happening in the what is the center of activity of the signal and how far the activity is spread. So, that is that's a vital piece of information, because let us say I am looking at I am searching for faults in a signal, then I would like to know these two pieces of information at least: around what time the fault occurred or this particular feature of interest was present in the signal, and how long was this feature present. These are the two at least vital statistics, so to speak, of the signal that I am interested in. I am also interested in knowing what are the frequencies contained in the signal whenever it was active, and for that I turn to the energy spectral density, as we have learned earlier also. But what we have learned earlier also is that this bandwidth can be misleading. So, if you look at these two plots here, we know already that the signal wherever it is active has only a single frequency over this region here, but the energy spectral density is not reflective of this reality. If I just look at the energy spectral density without paying attention to the signal, then I am compelled to believe that there are many frequencies present in the signal whenever they were present. So, there are two problems here: one, that I do not know when these frequencies were present, and two, it's not just showing the frequency that is contained in the signal. Of course, the center frequency still coincides with the actual frequency content of the signal whenever it was active, but then I have this spread of frequencies which is now giving me some misleading information. So, I am compelled to believe that there are frequencies apart from these 2 cycles per second. So, these are the two problems of using the energy spectral density to determine the frequency content and particularly the location in time of that particular frequencies of those particular frequencies that the energy spectral density is indicating. Of course, what I can do is I can keep the energy density in time and the spectral density by side by side and then examine these two plots, but common sense tells us that it is not going to be a useful exercise in practice, because in reality signals may have more than one frequency component, in which case, and also the frequencies can come and go. This is a very simple example, therefore, it is easy for me to determine what is happening by a visual inspection, but in practice it is going to be very difficult, and that is the main motivation for turning to time frequency analysis, which will tell me what frequencies were present over a given interval of time. All right. Now, we will look at one more motivating example which tells us the limitations of using spectral density or bandwidth. So, before I again go over this example, let me take you back to this example itself, so that I can introduce to you at least the concepts of amplitude modulation and frequency modulation. So, if you look at this energy density here in time, it is representative of what is happening in the signal in time. Wherever the energy density is 0, the signal has 0 activity, wherever it is non-zero, it has non-zero activity, or there is something happening in the signal. Now, if you look at the beginning and the concluding portions of the signal, there is no activity. I can look upon these two portions in two different ways. I can say that in these regions the frequency of the signal is 0. So, regardless of the amplitude, the signal will have what we say is 0 activity. All right. Now, of course, we can also say now that the signal had some frequency, we do not know what frequency it had, but then the amplitude of that signal over that period of time, whether it is here or towards the end, is 0. Remember, the signal in the signal representation for a periodic signal, I have A cosine omega t, or a slightly more generalized representations A of t cosine of theta of t. So, I could have A of t being 0, or I could have the frequency going to 0 and A being non-zero. So, I could actually represent the signal either as amplitude, whenever I have change in frequency or change in frequency content, I can in principle represent the signal either as amplitude modulation or frequency modulation. The main point in discussing the limitation of spectral density is the bandwidth is unable to tell me, in fact, the spectral energy spectral density is unable to tell me whether there was a frequency modulation or amplitude modulation, and time frequency analysis will help us discover that. So, this is an example in that direction. I have 4 signals, all of which have the same bandwidth. The expression for the signal is given on the right hand side at the top. All these 4 signals, as we will also see in the next module, will derive formally, I will give you the expression for the bandwidth for these signals, the value of this bandwidth. All these 4 signals have the same bandwidth. However, now you can see that their time domain profiles are completely different. This is an example that I have taken from Cohen's book. In fact, most of the discussion in this module and probably in this unit itself is going to closely follow the introductory chapters of Cohen's book. So, this quickly tells me that just by looking at the bandwidth or the spread of the energy spectral density alone, I will not be in a position to comment on what is happening in the signal. So, you can see these two this plot here is an example of an amplitude modulation, and here also I have an amplitude modulation. In some of the signals I have both amplitude and frequency modulations and so on. We will see this later on. Once we derive the equation for the bandwidth, we will revisit this example. So, the message is spectral density, energy spectral density, or even for that matter power spectral density, will not give me the time varying nature of the frequency content of the signal. And as a preview to the bandwidth equation, let me tell you that the bandwidth has contributions from both amplitude modulation and frequency modulation, and you could adjust one for the other to get the same bandwidth. That is the basic limitation of bandwidth. So, having discussed this time varying frequency content feature of signals, it is time to define what is known as stationarity for deterministic signals. Now, the Fourier transforms, especially the spectral analysis for the determination of frequency content, is ideally suited only for stationary signals. What is this stationarity? The stationarity is a property of the signal which requires that the spectral density remains invariant with time. That means the frequency content should not change with time. That is a very important and a very strict requirement for the suitability of Fourier transforms. In fact, if you think of it, most signals in reality may not even satisfy this stationarity requirement. So, let us look at this example from our introductory slides, where I have the signal with two frequencies in succession. In the first example, I have low followed by high, and the second one I have high followed by low. Given beneath are the spectral densities. You can see that the spectral densities look alike. So, it is unable to distinguish this switch of frequencies or the changing frequency content, and we say these two signals are non-stationary in a deterministic sense. You can you also encounter this definition of stationarity in the context of random signals, where again you can define, you can have a similar definition, and you can say that the random signal is stationary. In particular, we say second order stationary if its spectral density remains invariant with time. Okay. So, similar definitions therefore exist for both deterministic and stochastic signals. So, the main motivation for turning to time frequency analysis is to know how to analyze or to analyze the class of non-stationary signals. So, that is something to keep at the back of the mind. Okay. So, we had early on mentioned that the way I use the energy density plots or the spectral density plots and so on is I search for a particular feature in these density plots. In particular, I am interested in knowing when a particular feature existed in the signal, and the energy density is a reflection of what is happening in the signal. So, I want to know when a particular feature existed and how long this particular feature existed. Now, we formally introduce terms that will help us quantify what we are searching for, both in time and frequency. The first quantity of interest is the mean time, which is a measure of the center of activity of the signal. Now, again here, as I mentioned earlier, these definitions become easy to follow if you are able to recall the analogy of probability density functions for a random variable, where we talk about mean, variance of a random variable based on the probability density function. So, let me actually show you the similarity of this expression for mean time with the mean of a random variable. So, here I have for a random variable x, okay, do not confuse this x with the signal x that we are using. If this random, let us assume that this random variable is continuous valued, so that I can think of a PDF. Normally, by convention, PDFs are denoted by lower case, and we use a lower case x here. So, this is the PDF of this random variable, and when I want to know the expected outcome of the x or the center of the all possible outcomes of x, then I turn to this measure called mean or expected value or average value, which is defined as the first moment of the PDF. In this definition, we again integrate over the entire ensemble space. So, minus infinity to infinity here in this case refers to the extreme outcome. So, you are looking at the entire outcome space. Now, strictly speaking, there should be an integral f of x dx in the denominator. However, normally all PDFs are normalized to have unity area, so that the probability of the occurrence of any occurrence of this random variable is normalized to unity. Therefore, in many textbooks you do not see this denominator appearing in the definition of mean. The same applies to the definition of mean time as well. So, here we have mean time. So, now you can see the similarity. Now, here x, now instead of x we have time t. It does not mean that time t is a random variable here. Please notice that I am only giving these examples just as an analogy, but not they are not necessarily identical. So, now I am interested in the mean time of a signal x that is governed or that is given by the first moment of this energy density in time. Again, ideally I should have an S xx of t dt, but if you have normalized the signal to have unit energy, then you can switch off this denominator, and which is what I have assumed in the definition as well. Therefore, we will omit this, but you should keep at the back of your mind that there is a denominator, and you should certainly make sure that the signal has been normalized to have unit energy. Now, we know the definition of the energy spectral density. That is it. So, this is what I have from minus infinity to infinity over the entire existence of the signal. So, what does this give me? This gives me an idea of the center of activity of the signal. This is the mean time. Okay. So, I hope now that is clear. That is the analogy of mean time with the mean of a random variable is clear, and likewise we will you can extend these analogies to the second central moments that we shall discuss shortly. So, there is an example here at the bottom for a rectangular signal. This rectangular signal extends over this period t1 to t2. So, that is the duration over which the rectangular signal is active. Outside this interval it is 0, and I have here 1 over root t2 minus t1. You should verify that the signal given by this expression has a unit energy spectral density. It is fairly obvious. Therefore, I do not need to divide by this denominator in calculating the mean time, which is shown here. The mean time here turns out to be half of t1 plus t2, which agrees with our intuitive understanding of the center of time. When I have a rectangular signal within this interval t1 to t2, obviously the center of activity has to be at t1 plus t2 by 2. Therefore, this expression really gives me the correct answer. But for more complicated signals, this is a very simple signal, these expressions are going to give me the correct answer, but my problem will be to arrive at the intuitive answer, because the rectangular signal is a very symmetric, it is a very flat signal and so on, but in practice signals are going to have complicated shapes. Therefore, I need to have a feel for the answer, and that is going to make it difficult. The best way is therefore to calculate the center of time using this expression. All right. You will have plenty of opportunities in the assignments to evaluate the center of time for other signals as well. So, we turn now to the second central moment, because just knowing the center of activity of the signal is not sufficient. I need to know how long this particular feature or activity was present, and naturally I turn to what is known as the spread or the second central moment, again in analogy with the variance that we have for a random variable. Variance of a random variable is also the second central moment evaluated using the probability density function. So, it is denoted by sigma square t. This definition is hopefully straightforward here, t minus mu t square, the average. So, the brackets notation, sorry I had not mentioned earlier, the left and right angle brackets here denote averaging operation, similar to the expectation operation that we conduct for random variables. So, central moment, it is not simply average of t square. Again, I use the energy density to compute this second central moment. It is fairly easy to show, like we show even in the case of random variables, that the spread can be written as average of t square less the square of the average. So, that is a very standard result to show. Here as well I have assumed that the energy density has been normalized to have unit area. All right. Now, a big word of caution, this is not the variance of the signal. Just because I see a symbol sigma square t here, This is not a variance of signal. In fact, the subscript t should tell you that I am evaluating the variance here in the sense of time, not for the signal, and again time is not a random variable here. So, let us not draw some absurd conclusions from this expression. Now, this positive square root of this variance is called the standard deviation, and it is a measure of the duration of the signal. Again, for the rectangular signal, the standard deviation is given by 1 over 2 root 3 T2 minus T1. The way you look at interpret the standard deviation is the same way that you do for random variables. The standard deviation will give me a measure of the spread. It is not the entire spread itself. So, for example, if I have a Gaussian distributed random variable, that means if my PDF looks like has a bell shape, then approximately 95% of the outcome space or is actually covered by 2 standard deviations, right, and 3 standard deviations will cover 99% and so on. The same applies here. If the energy density here is a bell shaped one, then 1 standard deviation will give me an idea of about 66% of the signal's overall actual duration in time and so on. One thing that we can definitely say is if sigma t is large, then the signal duration is also going to be large. However, the actual interpretation of sigma t with respect to duration depends on the shape of the energy density. Like in the case of random variables, if I have if it has a chi-square distribution, a random variable, then the sigma t does not necessarily straight away give me a complete idea of the duration, but it is still a representative of the overall existence of the signal or the duration of the signal. Okay. So, henceforth we will say here by duration we will always mean sigma square t. So, it does not, duration does not now refer to how long the signal existed, but exactly the sigma square t, and mean time being the one that we have defined earlier. Now, before we move on, here I would like to give an expression for the average of a function of time that can be useful in many situations. This is again the same expression that we encounter in the context of random variables, where I find expressions for expectations of functions of random variable. There you would have g of x, and instead of this time averaging, I would have averaging across the ensemble space, and I would have in the integral g of x times f of x dx. This is useful in certain calculations that we may find later on. Now, here is an exercise that I give from Cohen's book. Given the signal, I invite you to calculate first the constant A, so that the energy of the signal is total energy is normalized to unity, and then compute the average time and verify with the theoretical answer. By looking at this expression here, you should be able to say what is the center time, and also compute the standard deviation. Again, by looking at this expression, you should be able to say what is the spread of the signal in time. Okay. So, with this we move on. This is a simple exercise, homework exercise for you. Now, we turn to the frequency domain and we ask what is the center frequency, which again we have used this term center frequency before when we talked about complex Morlet wavelets and when we were discussing the scaling property of Fourier transforms. So, here is a definition of the definition of the center frequency. It is the first moment of the spectral density, exactly along the lines of the mean time that we had defined, and once again we assume that the energy spectral density has been normalized to have unity area. The rest of the interpretations is straightforward. Again, omega is not a random variable here. We are just calculating average of omega with respect to x, and we are integrating in the same way as we do for the mean time, except that I replace x of t square, mod x of t square with mod x of omega square and so on. Now, this following trick that again I give from Cohen's book typically aids in the computation of this integral. That why this is a nice expression, because in order to evaluate the mean frequency, I do not need to evaluate x of omega first. If I am given the signal expression, I can actually straight away compute the mean frequency without having to go through the step of computing the Fourier transform. We shall use this later on in deriving the equation for the bandwidth. Of course, when I say equation of the bandwidth, it is a later module. Here I am giving you the definition of bandwidth. So, bandwidth again is the second central moment of the energy spectral density, and again along the same lines as we had defined duration. Earlier we had said duration is sigma t. Now we are going to say that the bandwidth is sigma omega or sigma square omega, whichever way you want to call it. Duration also you can refer to as sigma t. Normally that is how it is referred, but sigma square t is also a legitimate representative of the duration. So, sigma square omega once again is based is defined as the second central moment of the energy spectral density, which again you can show is the difference between the average of omega square less the square of the average, and bandwidth is the positive square root of the spread. But when we talk of bandwidth equation, we will give an equation for sigma square omega, because they are easier, that is an easier quantity to work with. Now, if you consider this amplitude modulated signal as an example again from Cohen's book, the mean frequency calculation, if you plug in the signal into the expression for the mean frequency, you can use this equation 5 to compute the mean frequency. It turns out that you get omega naught, and it is fairly obvious here. This is what is happening here is this is a complex exponential here e to the j omega t, and then I have an amplitude modulation. So, the rest of the factor in x of t is amplitude modulation. So, the actual frequency present in the signal is omega naught only. This is what we had seen in the first example or the opening example of this module, where I had a complex sine wave for a certain duration, and then front and the end there was no activity. So, you can say there was an amplitude modulation. If you recall the energy spectral density that I had shown, the center frequency of this is still 2. So, it turns out all right. The only issue is with respect to the bandwidth. Ideally, I should have expected a nice spike there, but I will not, because I am going to have these components here contributing as well. The one of the ways of looking at it is, of course, as we have explained earlier, the bandwidth has contributions from both amplitude modulation and frequency modulation. The other way of looking at it is Fourier transform imagines a signal to be made up of several weighted sinusoids at any point in time. Now, what happens is when the signal has 0 activity, that is where it has an issue. It imagines the 0 activity signal to be as if there are sinusoids cancelling out each other. So, it represents the 0 part of the signal as an addition and cancellation, a subtraction of sinusoids, which is not necessarily true. As a simple example, if I am standing outside a room and I do not hear any sound from the room, I can think of 2 possibilities at least, that there is no one in the room or nothing in the room makes any noise, or there are at least 2 people in the room or 2 sound sources in the room which are actually cancelling out each other. Now, what is the actual reality? You have to go into the room and check. What happens is Fourier transform always imagines this 0 activity or this no sound region to be made up of several sound sources cancelling each other. That is why it tries to bring in other frequencies to explain the 0 activity signal. That is the main limitation of Fourier transform. So, let us return to the example. Here I have the mean frequency calculation already discussed. Now, the bandwidth equation gives me alpha by 2. Now, you see the alpha belongs to the amplitude modulation factor. You can now see that the bandwidth has contributions from alpha by 2. So, the moment I have amplitude modulation, I will see a spread. Ideally, I was not supposed to see the spread, but that is not incorporated into the Fourier transform. Both amplitude modulation and if there was a frequency modulation to the signal, that would have also appeared in this expression for the bandwidth, which is what we are going to see in the bandwidth equation. Okay. So, let us conclude this module with a couple of examples in MATLAB, and which will give us the motivation also for looking at analytic signals later on. So, this is an example illustrated in MATLAB using the time frequency toolbox. I have given the reference to this at the end of the lecture. I have generated amplitude modulated signal here. As you can see here, FM lin will give me a simple sinusoid, and I am modulating that with an amplitude model. Sorry, FM lin will give me a linear frequency modulation, linear chirp, and that is being modulated by this Gaussian amplitude modulation. And I am plotting the real part of the signal. By default, you will obtain a complex valued signal in the time frequency toolbox when you execute these commands. And there are two routines in time frequency toolbox for computing the duration, mean time, and bandwidth center frequency. These are LOC time and LOC frequency. Again, I welcome you to type these commands by yourself, and if you make mistakes, that is good, it is a good learning experience, but if you do not also, it is good. But it's please go through these commands one by one. And what I show you here are the energy densities in time, and here at the bottom energy spectral density. You can clearly see that the duration, the center frequency comes out all right here, that as I have used. In fact, you should get these values and verify, that is run these routines LOC time and LOC frequency, and verify that the answers that you get for T and B coincide with the give you a fairly correct idea of the duration of the signal and the bandwidth, and that the Tm, which is the center of activity here, you should upfront determine manually what is the center of the activity here. That would be the average of these two time instants, because it is a symmetric modulation that we have introduced, and the average frequency being here, you can read off, and you should check that Wm tallies with the center frequency given out by this energy spectral density. It is a symmetric one. Therefore, whatever you visually observe should more or less coincide with what you get from the routine. Okay. Now, let us turn to an interesting example, which is a concluding example in this lecture. I am going to take a sine wave, right, of this long. So, it is present over the entire existence, single frequency, no amplitude modulation. The center time should be this somewhere here, that is the mean time. But the point that I want to draw your attention to is the center frequency. If I look at the energy spectral density that I am showing you here, of course, you may think of a power spectral density, but we are looking at a finite duration sine wave. We will not worry about what is happening outside, you can assume it is 0. Therefore, let us talk of energy spectral density. I show the energy spectral density here. You can see that there are two peaks, symmetric peaks around 0, right. So, if you look at the center frequency manually, it should turn out to be 0, which is right. In fact, it will tally with the value given out by your LOC frequency, LOC freq. It is actually going to return a value of 0 for Wm, check it out for yourself. Now, that does not make sense. How can the mean frequency of a sine wave be 0 when I know very well that the sine wave has a non-zero frequency? So, what is the issue here? The issue here is the way I have represented the signal in computing the center frequency. This is where if I turn to a complex representation. So, x of t is the given signal. I am going to construct a complex representation. Recall the one of the lectures in unit 2 where we talk of signal representations. I am going to construct a complex representation of the signal whose real part is the signal itself, imaginary part is a Hilbert transform of the signal, which put together this complex signal is known as the analytic associate or analytic representation of the signal. When I work with z of t instead of x of t, then I have this energy spectral density for z of t, and it correctly gives me the center frequency, not only manually, that is by visual inspection, but also when I use the LOC frequency, you can check that WMC, which is the center frequency for the z of t, exactly coincides with the frequency that I had used in x of t. So, this motivates us to look at complex representations, which we call as, in particular, this complex representation which is known as the analytic associate of the signal x of t. So, that brings us to the close of this lecture. and in the next lecture, which is 4.2, we will derive the bandwidth equation and also study the concept of instantaneous frequency. So, these are some of the references for your perusal. You should go through this. The time frequency toolbox reference is given even in the introductory slide, or you can look up the next module as well. Thank you.